Alright, in this video we want to find all of the critical points of f of x equals sine of pi x on the interval -2 to 2 and determine if they are local max or local min. We also want to give the intervals in -2 to 2 where the function is monotone, and give the intervals where f of x is concave up. So let's start with finding the critical points. So remember, finding the critical points means we want to find where is f prime of x equal to, start by the derivative. So the derivative of sine of pi x is cosine of pi x times the derivative of pi x by the chain rule. So that is equal to pi. So we have pi cosine of pi x. So this is what we want to set equal to 0. So we have pi cosine of pi x equals 0, which means if we divide both sides by pi, we have cosine of pi x equals 0. So when does cosine equal 0 becomes our question. So we know that cosine of any argument is equal to 0 when that argument is plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, any odd multiple of pi over 2. So what we really want to say is that we want pi x to equal one of these multiples of pi over 2. So for example, pi x equals pi over 2, so x equals 1/2 would be a solution. But we need to do as many of these as will fit inside of our domain, which again is -2 to 2. So if we do this a little more generally, we have pi x equals plus minus pi over 2 yields plus or minus 1/2. Okay, both of those are in our domain, so those are good. We have x equals plus minus, pi x equals plus minus 3 pi over 2, which when we divide by pi gives us x equals plus minus 3/2, also in our domain because 3/2 is between -2 and 2. We have pi x equals plus minus 5 pi over 2, which when we divide by pi gives us plus minus 5/2. Now, both plus and minus 5/2, if you'll notice, are outside of our domain, so we don't have to worry about these. So these are our critical points. Okay, we have 4 of them. So we have x equals 1/2, -1/2, 3/2, -3/2. So we need to find out now, are these local max or are these local min? So there's a couple ways to do this, so let's do them both ways, but let's start with the first derivative test. The first derivative test says that we plot our critical points. So we have -1/2, let's start with -3/2, -1/2, 1/2, and 3/2. And let's pick points on either side of all of these. So over here, let's take, let's see, we want something between -2 and -3/2. Doesn't really matter. Let's just take -1.9. Here we can take -1, it'll work, 0, 1, 1.9. And then we want to plug each of those into our derivative. So remember, f prime of x is equal to pi cosine of pi x. So f prime of 0, we'll start with that one, equals pi cosine of 0. which is pi times positive 1. So we have the derivatives are positive in that interval. All right. Oops. So f prime of negative 1 equals pi cosine of negative pi, because we're taking pi times negative 1, which is pi times negative 1. So in this interval, the interval where negative 1 resides, we have negative slopes. Okay, so now let's look at f prime of negative 1.9, which is pi times cosine of negative 1.9 pi, which, if you type it into your calculator, turns out to be about 0.995 pi, which is a positive number. So over here, we have positive values. Okay, now let's go back over to f prime of 1, which is pi cosine of 1 times pi, and cosine of pi is negative 1, so this is negative pi. So we have negative values here. And finally, f prime of 1.9, which is pi cosine of 1.9 pi, which is also approximately 0.995 pi. Since pi is an even function, you get this nice symmetry. And so we have positive over here. So now we're ready to use the first derivative test to determine which one of these is a local max or a local min. So if you can't remember which way it goes, you can draw a little picture. So if our slopes go from positive to negative, we have a local max. And if they go from negative to positive, we have a local min. So this again is positive to negative, and this is negative to positive. So let's see what we have. So we go from positive to negative here, so we should have a local max. We go from negative to positive here, so we should have a local minimum. Positive to negative, max, negative to positive, minimum. So there's a local maximum at negative 3/2, a local minimum at negative 1/2, a local max at 1/2, and a minimum at 3/2. But there's another way we could have gone about this, which is to use the second derivative test. So let's see how that works. So the second derivative test says we take our critical points and we evaluate them at, we evaluate the second derivative at those points. So first let's find the second derivative. So if f prime of x was pi cosine of pi x, then the second derivative, f double prime of x, should be negative pi squared sine of pi x. So again, we have to use the chain rule here, so let's just show that explicitly. So it's pi, cosine becomes, okay, cosine becomes negative sine, and then we multiply by the derivative of pi x, giving us exactly this. So our critical points, let's write those down one more time. We're negative 3/2, negative 1/2, 1/2, 3/2. So we want to plug in each of these values to our second derivative. And the reason we can do that is, let's draw a little picture here again. At a local maximum, we know that we are concave down, which means that our second derivative is less than 0. Our second derivative is negative. So if we know if our second derivative is negative, we have a local maximum. At a local minimum, we're concave up, which means that our second derivative is positive. So if we find that our second derivative is positive at that critical point, then we know we have a local minimum. Okay, so let's do it. F double prime of negative 3/2 is negative pi squared sine of pi times negative 3/2. So that's negative pi squared sine of negative 3 pi over 2. And at negative 3 pi over 2, sine should be 1. So we have negative pi squared, which is of course less than 0. So at x equals negative 3/2, the second derivative is negative, which means we should have a local maximum. Let's see if that corresponds to what we have up here, and in fact, it does. Okay, let's keep chugging right along. So here we have sine of negative pi over 2. So sine of negative pi over 2, if we all remember our unit circle, is negative 1. So negative 1 times negative pi squared gives us pi squared, which is greater than 0. So at x equals negative 1/2, the second derivative is positive, which means we're concave up, which means we should have a local minimum. So let's check our first derivative test to see if it checks out, and it does. Moving right along. So we have negative pi squared sine of pi over 2. Again, back to our trusty unit circle, sine of pi over 2 is 1, and we're left with negative pi squared, which is less than 0. So by the second derivative test at x equals 1/2, the second derivative is negative, which means we're concave down, which means we have a local maximum. Let's check to make sure we have that right. Indeed we do. Now for the last one. Okay. And sine of 3 pi over 2 is in fact negative 1, which means we have pi squared, which is greater than 0. So at x equals 3/2, our second derivative is positive, which means we have a local minimum. And once again, these derivative tests are consistent with one another. Okay, so now not only have we found where our local max and local mins are, and if they are local max or mins, but the first derivative test also gave us where the function is increasing or decreasing, where it's monotone. So if we look at the intervals where the first derivative is positive, that tells us our intervals of constantly increasing. So we can go ahead and say that f of x is monotonically increasing on -2 to -3/2, and negative 1/2 to 1/2, and 3/2 to 2. And monotonically decreasing and the negative intervals, so negative 3/2, negative 1/2, and 1/2 to 3/2. Okay, so now that we have that, we just need to figure out where's the function concave up. So if we want to find where it's concave up, we need to look and see where's the second derivative positive. So let's again look at our second derivative. Okay, so we want to find when is the second derivative positive and when is it negative. So we can do that by finding out when it's 0 and looking at either side of it. So let's find out when this is 0, also known as the inflection points of our function. So we want to set negative pi squared sine of pi x equal to 0. So we'll divide through by negative pi squared. We'll have sine of pi x is equal to 0. Now, when is sine of the argument equal to 0? Well, that happens when the argument is 0 plus or minus pi plus or minus 2 pi plus or minus 3 pi, etc. So we want to find out when does this happen in our interval, which, remember, was negative 2 to 2. So we can set pi x equal to 0, which means x equals 0. Okay, that's in our interval. We can set pi x equal to plus minus pi, which means x equals plus or minus 1. That's in our interval. And pi x is equal to plus minus 2 pi. So x equals plus minus 2. Okay, anything greater than that, 3 pi, 4 pi, 5 pi, will all be outside of our interval. So these are the places we need to look at. So let's draw a number line of our x values. So let's put x right in the middle. X equals 0, x equals 1, x equals 2, negative 1, and negative 2. So really, we don't need to check anything out here because that's outside of our interval, so we don't care about it anyway. So let's pick points in between. So we could pick negative 3/2 for this point, negative 1/2, 1/2, and 3/2. Let's see what we get. So our second derivative was negative pi squared sine of pi x. So let's just plug in these points. F double prime of negative 3/2 is negative pi squared sine of negative 3 pi over 2. We plug in 3/2. So it's negative pi squared. And sine of negative 3 pi over 2 is positive 1, which makes the whole thing less than 0. Okay. F double prime of negative 1/2 is equal to negative pi squared sine of negative pi over 2 negative pi squared, sine of negative pi over 2 is negative 1, which makes this pi squared, which is positive. F double prime of 1/2 is negative pi squared, sine of pi over 2, which is equal to negative pi squared. Sine of pi over 2 is 1, so that makes the whole thing negative. And f double prime of 3/2 is negative pi squared sine 3 pi over 2, which is negative pi squared times negative 1, which is greater than 0. Alright, so let's put those back on this number line. So in the region with negative 1/2, we have positive. In the region of positive 1/2, we have negative. And in the region of 3/2, we have positive. So what this tells us is f of x is concave up on the intervals -1 to 0 and 1 to 2.